like to think about finding the mean from a frequency distribution. What we've been doing is finding the mean from a list of data, but this time we're going to be given a frequency distribution. This time we're given the tar in milligrams in non-filtered cigarettes and the frequency of those for cigarettes. So we have several different data ranges. 10 to 13, 14 to 17, 18 to 21, 22 to 25, and 26 to 29. Alright. One cigarette who had between 10 and 13 milligrams of tar, 0 cigarettes with between 14 and 17, 15 with between 18 and 21, 7 between there, and 2 between there. So this frequency could be better described as number of cigarettes in that range. So there's our full problem. We're going to find the mean of the data summarized in the given frequency distribution. For that, we're going to use formula 3-2, which says x bar equals the sum of the frequency times x divided by the sum of the frequencies. I'm going to write that in cursive too. So what we're going to do is take 1 times some number in here. What number do we use? It says x, but that's kind of non-specified. We're going to use the class midpoint is what it says to use in the book, so we'll use that. Halfway between 10 and 13 is 11.5, and similarly halfway between 14 and 17 is 15.5, 19.5, 23.5, and 27.5. What we're going to do with this formula then is take the sum of f times x divided by the sum of f. Let's get that denominator first. The sum of f is 1 plus 15 plus 7 plus 2. That's the sum of those things. And then the sum on the top is 1 times 11.5, 1 times 11.5 plus 0 times 15.5 plus 15 times 19.5 plus 7 times 23.5 plus 2 times 27.5. Now we're going to add all of those products together. Oh, you can see the end of it, can you? And so 20.94. Now we're supposed to compare that 20.94 to the original data. 20.94, and the 21.1 is fairly close. I will tell you though, and anyway, remember this 13 was chosen as just a number that would contain the set. We could have chosen 13.999 for the class upper limit. So if we had chosen 13.9999 as the upper limit, then we would have been using 12, 16, 20, 24, and 28. And if we had done that and ran through this calculation again with the 12, 16, 20, 24, and 28, we would have just added 1/2. We would have been adding 1/2 to each of the members of the group, so we would have added 1/2 to this number here. 20.94 plus 0.5 is 21.44. and this just would have been closer to the actual answer, 21.1. No, on second thought, the 20.94 is just a little closer. If I take 21.44 minus 21.1, I get 0.34. Or is 0.34 off. If I take the 20.94 minus 21.1, I get 0.116. Difference. Let's see, different equals difference, and what was it? 0.16 equals the difference. So yeah, the difference. Actually, the using the so it appears that using the class midpoints give a better estimate for mean than using numbers halfway between consecutive lower class limits. So I'm kind of surprised by this, and I'd kind of like to reason out why, but I think the main thing is to consider is that what I'm thinking of is this is going from 10 to 14. This going from 10 to 14, 14 to 18, 18 to 22, 22 to 26. And the way I should be thinking of it probably is thinking of it more like going from 9.5 to 13.5, 13.5 to 17.5. And then in that case, if we're thinking about going between consecutive class boundaries rather than consecutive lower class limits, then we would get this 11.5, 15.5, 19.5, 25.5, and 27.5. But you can see this is one reason that statistics may be part art, part science, because you could easily decide to use as your class boundaries 9.9999 to 13.99999, and you'll get a different value for these for your mean from the frequency distribution.